Hi, everyone, and thank you for attending today's webinar, Needle Movers First, Strategic Early Decisions that Define Solar Project Success. I'm Kelly Pickerel, Editor-in-Chief of Solar Power World. And before we get started, we're going to go over a few housekeeping items. You can download the slides and any additional resources for today's presentation in the resource window on your screen. We will have a Q&A at the end of the webinar, so please submit any questions in the Ask Question window. If we do not get to your question, our presenters may reach out to you afterwards. You can also expand your view of the slides by using the icon in the top right corner of the slide widget. All of the boxes on your screen can be moved and resized to meet your preferences. And finally, if you are watching this webinar on demand, you can still use all of these features, including sending questions to our presenters. If you experience any issues during today's webinar, try refreshing your browser tab. If you continue to have problems, try closing other apps and browser tabs that you may have open. You can click Help in the top menu for more troubleshooting steps, or you can ask our producer for help via the Ask Question widget. So let's get started with today's webinar on early layout decisions. I'd like to thank PVFARM for sponsoring this presentation. Today, we will hear from Maxim Markovich of PVFARM. He does a lot of webinars with us, so this is going to be a good one. So now I'll turn it over to Maxim to get us started.
Thank you. Appreciate it. Thank you, everybody, for joining us. Really pleasure to do this. Really pleasure to have the conversations after the webinars, and always appreciate your addition to our philosophical topics and our philosophical findings. So thank you for that. So today we're going to talk about needle movers, and basically we will start with what are the needle movers. So this is basically the factors that define the biggest impact on design outcomes, the risks and challenges you have to handle early, and the points where you hand it over, like basically the deliverables or documents between the subject matter specialists or the strategies which you need to test basically before you move forward. So essentially those are kind of parameters that you need to take care as early as possible in the process. And as you know, there are like million parameters you can tweak when designing solar PV layouts, but only a handful of them are kind of decisions that make or break success. And also I would add here that usually the first 10% of your solar layout is basically equal to 90% of your success. So the amount of considerations, the amount of kind of risk analysis you can do, it all will actually pay off late in the process, and that's what we'll have to talk about. So what's the thing about needle movers? And I think the most annoying and also amazing part of them is that they are change. They are not fixed, and they depend on the context. They depend on the site boundaries, terrain, specific project information, meteo file, specific requirements, client preferences, etc. So, and also they not only kind of vary from that context, but they also shape the workflows that teams needs to follow in order to get the best possible design of the solar PV layout. So we usually define 3 levels of analytical depths. So the first level is obvious. The second level, the rules of thumb. And then the third level is the strategic optimization. So the deeper you dig in terms of like layout design, the more pleasant optimizations, the more efficient layouts you usually find. So let's talk about every level of those of the analytical depths. So the obvious is obvious. It's a common thing. It's common sense things like the stuff that on the surface, well understood. So if you have a fancy steep terrain, that basically means you need to optimize your layout around cut fill, grading, and stuff like that. If you have a tough voltage drop requirements, you basically need to focus on ideal blocks, electrical blocks, and usually those things are extremely obvious. And that's the first level, right? This is where people start. So the second level is basically rules of thumb. This is more like industry standards. That's when people rely on familiar standards and habits that produce acceptable results, something that worked in the past. Those rules of thumb, they're usually used when teams, they don't have like enough time to actually do a proper analysis or to consider multiple different options. And those things, they usually well known on the industry level, but also they are well known for the specific company, like EPC contractor or developer, that worked really well in the past. So for example, using central inverters, no matter the site context, or sticking to a specific block configuration that worked last time. We'll show you a couple of those examples. So let's say we have a different types of boundaries, and we know a bunch of people who design solar PV layouts, and they have different recommendations based on the different site contexts. So let's say you have big box and easy, medium chunky puzzle, and complex Swiss cheese. So based on those site characteristics, and all of them actually might be described numerically or mathematically, but it's funnier to keep it that way. So, and essentially, you basically, let's say, have a bunch of different blocks configurations. That's what you can see on the left. Okay, so that all of those block configurations, they have, let's say, for example, combiner box for 100 amps, central inverter, transformer skid, and you see like 4 height block, 3 height block, and then basically 2 height block. And so basically trying to fit those blocks in a different boundaries, assuming we are not allowed to basically to have like blocks of a different type and different size. So that basically will give us a completely different results based on the site complexity, based on the boundaries complexity. For example, for a complex Swiss cheese, 2 height block was the best one. So basically, it's essentially sorry, not a 2 height block, 3 height block. That's this option, right? So you can see 9 blocks, 34.3 megawatts DC, land use ratio 75. So for a medium chunky puzzle, for example, 3 height block is preferable. Again, same story, right? So this might be preferable, but at the same time also like the 2 height block might work the best, essentially. And then for a big box and easy site, it's actually it's not clear. You can see here, for example, that in terms of DC capacity, this block actually wins, but in terms of land use ratio, it's 95% against 97. It also wins, but it's funny that, for example, when you use like 2 height blocks, you actually need to provide more access to the site. So essentially you will have more rods, which basically might produce some unexpected results. And in some sites, big and boxy and easy, you might have a side stretch in the north-south direction, and then basically the block number 1, 4 height block, would works the best, especially mixing it with the preferable electrical architecture. So let's say if your team, if it's a construction company and the team prefers to have a harness combined architecture, then probably the block number 1 would be the best, assuming that you hit the target. And if the site is stretched in the north-south direction, you will have, that's the way you will have the minimum number of east-west roads to provide access. So essentially those like, based on some proxy, some kind of site description, you can come up with a certain rules of thumb that will kind of give you generally good advice to start with. And so now we're going to talk about the third category, which is basically strategic optimization, or we also call it advanced trade-offs. This is the place where basically the biggest opportunities are. It's going beyond heuristics by testing multiple scenarios across multiple disciplines: civil, electrical, structural, layout. And those usually kind of expose a very hidden trade-offs. Examples of such advanced trade-offs are, for example, cut fill versus piles optimizations, where you control the gradient window to find the best balance, rigid versus terrain following trackers analysis, wind exposure analysis. You might hit, for example, you might hit the DC target by shifting trackers or using more lens types. However, this will make your shifted trackers, they will be easier exposed to the wind, and as a result, they will have heavier piles. So basically, you need to test whether it's going to work on overall cost. Another example, optimizing for blocks versus optimizing for grading. So basically, when you optimize for perfect blocks, you usually kind of stick to electrical efficiency. When you optimize for grading, you can, get whatever you will be very surprised with, right? So also optimizing for DC capacity versus optimizing for buildability, and being in piles, like, there are basically many trade-offs, like hundreds of trade-offs that can be considered later, like, but there are like those specific ones that needs to be taken care as early as possible. So I'll just show a bunch of interesting findings. We'll try to keep it 2D, just to make it simple. So this is an interesting example. So on the left we have three blocks we used. On the right we have 2 types blocks, right? So it's a 3 height, 2 height, and 3 height inverted, 2, 3, 4 on the left, and essentially 4 height and 3 height blocks. So as you can see, we get basically the same DC capacity, different rods configuration, different blocks, but the same DC capacity, and also like different number of blocks in the different parcels. So basically, if you have such situation, and if you know that, let's say your target, as in this example, 891.6 megawatts DC, then obviously the choice would be the one that gives you the cheapest DC collection, and it depends on many factors. But basically, that's interesting to keep that in mind. That with the same side boundaries, it's just you can have a completely different block configurations which will work in the same way, and then the exercise actually to figure out which pair will give you the best electrical wiring. Another interesting finding is that you can see it here. We use like block 1 and 2 on the left, and block 1 and 4. So literally on the right. So those are literally the same blocks. The only difference is block 2 and 4. They're kind of inverted, which is really funny, right? So the difference in those blocks in general is basically, if you think about that, the skid will be either on the north side or south side of the rod. So the difference is that how many cables will cross the rod, which will be probably expensive part of the low voltage design, and there will be trench there, etc. Right? So let's say, assuming you have so basically, assuming you have a northern hemisphere or southern hemisphere, you will have a different preferable skid position, which will give you a different preferable kind of block configuration. And you can also see like doubling down that actually the left configuration, which was completely surprising, gives like almost 4 megawatts DC more than the right one, assuming you minimize for rods. So those findings, there is no way to actually come up with a rules of thumb or like specific kind of experience, because it's just, you can figure out it only when playing around and basically seeing what's happening. Another interesting case here where we optimize for repeatability, or we can call it buildability, on the left, again using 4 types of blocks, and then basically seeing how much DC we can squeeze out of the side, and optimizing for DC capacity on the right. So when we were optimizing for DC capacity on the right, we basically populate layout with trackers first, and then we did the blocking, and as a result, we got like 65 block types, which is again gives you 809 megawatt DC versus 709 on the left. But the number of blocks you need to use is crazy, and that's perfect. That's a good example where like the right balance needed to be found. So yeah, so coming back to our levels of analytical depth. So I would say the obvious still needs to be checked, as the market is fast growing, solar PV is fast growing market, new equipment, new racking, etc. As for advanced trade-off or strategic optimization, it's good when the findings people basically getting on the real projects, they basically enrich the specific company-wide rules of thumb. So basically, not the like general market knowledge, but that's what we can see among advanced customers like EPC contractors, sophisticated developers, engineering consultants, when they have capabilities in-house to actually to do those sophisticated trade-offs. So they usually enrich their rules of thumb in order to proceed with the next projects. So that's why now I just want to wrap it a little bit, showing the needle movers framework, the one we presented on our last webinar that was related to electrical parameters, and we went into kind of large details there. Today, we just basically wrapped it in a shortest possible version, and you guys will be able to download it as a PDF and to try to use it. So basically, how do we define those parameters that are the needle movers. And so what we suggested is basically the framework which has 3 dimensions for every single parameter, which is first one, cost impact. So basically how much this parameter influences the total system cost. For example, module choice, how much does it do that? So design lock is how hard it's, lock-in risk is basically how hard it's to change this decision later in the design construction. And then the third one, system interaction. So how many other design elements this parameter affects or constrains. So just a couple of examples, like what do you mean about those parameters? Those parameters are usually things you can tweak in terms of like discipline-specific parameters. And it's also kind of quite hard to define discipline-specific parameters because especially when you talk about layout, all of them are connected to the neighbor disciplines. But examples like, again, tracker mix, tracker shift, so you can mix different trackers, you can shift your trackers, you can align your trackers, you might have a specific blocking strategy or specific layout architecture, like let's say skids along the roads or versus nested architecture. There might be different inverter mix, different block aspect ratio, and many things like that. Those are examples of like layout parameters. There are also like plenty of examples of electrical engineering parameters. Wire sequence, combiner box, load break disconnect position, clustering, row grouping, module selection, boundaries, complexity, row height, block footprint, so like plenty of parameters like those. And among the, so basically we have chunks of those parameters which basically vary based on the software you use. But essentially, the more configurability you have, the more chances you have to spot those essentially needle movers, those the most kind of important things to think about as early as possible. So that's basically the parameters, right? So what we did in the past webinar, we basically used controlled comparison method. So this is a, instead of like using correlation or anything sophisticated like that, we basically were locking all of the variables except, let's say, except the one. And then we were testing like worst versus best. And then we were defining the swing of the cost. So basically we were measuring, normalizing and measuring the swing of the cost. So just a good example of that, you can see row height parameter, which is might be also called block height, which defines essentially row height or block height together with your inverter loading ratio or DC-AC ratio is actually defines approximately the block footprint. And so then block footprint and let's say electrical pattern you use, let's say harness or combiner, harness and combine architecture versus trunk bus architecture, it actually defines the cost of the low voltage system. For example, we locked it on the left, you can see basically 2 height blocks, and then on the right you can see like 5, 6 height blocks. And we used a specific electrical pattern, and we can see that it was like 1.8 million saved, almost 10% in electrical cost. You can see electrical cap is 13 cents versus 14 cents. So essentially, it doesn't matter which one is better at this stage. It's just what matters is that this parameter gives you this swing. So you will understand the importance of these parameters. And so basically, the way you do it with pretty much everything you have, and then you define which are the biggest players. And I remind those are only from a costing point, right? So we still on this first kind of dimension. So that's the way we basically run many different scenarios, and we define the cost impact for every single parameter that we are kind of testing, right? So after that, we go to the design lock-in risk, which is really different. It's about basically where do you want this parameter to be locked, meaning that changing it later will create too much troubles. And so let's say in terms of module selection, if you want your module selection to be locked as early as possible during feasibility study, you give it 5 points. If you find with like playing with wire gauge unification, meaning that you can like try different voltage drop strategies, different cables, and you can do it like really at the latest moment. If you can do that, you give it the basically the smallest value. So in that sense, you kind of get in those like values for design lock-in risk, and it's going to be different for different company, for different process. That's why we present it more like trying to do it in a more like abstract way. So it's kind of useful for people who likes doing sophisticated analysis. And then system interaction. So what it means is that basically changing of this parameter, how many other deliverables it's going to change. A good example, if you change the module, you need to redo everything, right? Energy, layout, blocking, electrical engineering, procurement, everything. So the highest value, right? If you change, I don't know, maybe row grouping or combiner box position, there are just a couple of things. So basically, again, defining the value, and then as a result of this, of those three dimensions, which we just discussed, I'll jump quickly. So cost impact, design lock-in risk, and then system interaction. We can kind of, summarize it and get like the final table where you can actually describe your like scored parameter list. So essentially, that's the framework for needle movers we presented last time, and we dive in a really huge detail. This way, today we want to go a little bit further and basically build on top of that. So if we go to the next slide, I just want to talk a little bit about like types of needle movers. So we discussed that there are like local needle movers, right? So let's say for electrical discipline, basically the pattern, the electrical pattern or the wire sequence would be a local needle mover. That's going to be a parameter which is going to drive the electrical discipline in general, right? But there are things, because those disciplines, they work together when they design layout. When people design layout, they collaborate a lot. There are those so-called global needle movers. Those are parameters that affect a couple of disciplines simultaneously. So there are plenty of good examples. We can grab this end-to-end vertical exposure when basically when one end of the tracker is higher than another one, there will be a wind, and then basically the tracker that has a higher end on the torque tube, it will be exposed, which basically what it means is that the piles will need to be heavier in order to hold it, right? So that's kind of a good example where, and again, you're doing kind of civil engineering in order to prevent this. This is why it's all connected, so it's in between civil and structural. However, the one thing that I want to introduce here is a workflow needle movers, because we can see that there needs to be kind of discipline that drives the layout. And if we will go to the next slide. So what I want to say is that we can see that there are so many people who basically logged their kind of workflows years ago when just solar PV started within that specific company, for example. And then those workflows are not being changed. So basically it's like a kind of tradition, or we used to do things that way. And that's, frankly speaking, what we want to talk a lot right now, and basically focus on this, the next part of this presentation. So essentially, you can see the tools evolution for designing utility scale solar PV farms. And, we will probably skip the draft board. It was a fun time. And basically, there are general purpose tools like AutoCAD or Civil 3D. So, and this is basically the tools that not designed for a true multidisciplinary collaboration. So they have a kind of limited analytical capabilities. I would say workflows rely on primitives like polylines or lines, and then no advanced tools to guide the decision-making process. And what we've built with PVFARM, for example, we tried to build a kind of Autodesk Revit for solar PV, which is basically like BIM environment with intelligent objects for designing solar PV farms. And essentially, and the reason for that is that the urgent need for true multidisciplinary collaboration. And so basically, because like the only way to actually, to exploring trade-offs across disciplines is an absolute must-have when designing solar PV layouts. And I'll probably run a quick video to explain what it means. So I will show a specific example of the workflow where you can see how kind of different disciplines can kind of flow from one to another, analyzing results and jumping back and forth and stuff like that. So let's go to the next one. You guys should be able to see the video which we made. Yes, okay. So look, that's the specific workflow. Let's say we'll start with running our first layout. So we're getting something. So we're getting our first layout, some DC, and we go and immediately checking how many trackers are exposed to the wind, meaning how many exterior, how many edge trackers. Then we go back and we have an option to align our trackers and basically seeing updates in real time. So wind load, analysis is happening on the background in a real time. So we don't need to wait for this. We need just basically to check the numbers and to go further. So then let's say we have some layout, we're gonna go and run cut fill analysis. Very simple, specific like north-south slope limitations, gradient window, reveal embedment. So we're running cut fill analysis and getting the proposed grade terrain, essentially getting some cut fill metrics, and we can analyze it, and then we get in runtime metrics for dirt and piles. Again, you don't need to go and kind of count them. They're already there in the system, being calculated as you go. So you can see, then we can go and quickly check the most heavily graded blocks. So what are the blocks, meaning transformer groups, where we have the biggest amount of dirt that needed to be moved. So again, it doesn't need to do any specific, terrain minus terrain, terrain plus terrain, isolation and stuff like that. Those metrics are already there, sitting, waiting for you to check and to make the right call and to go further. So the same as you go, and again, you are not noticing, but due to the project setup, your energy model is another thing, which is a clearly metric. You place the trackers on the terrain, and you can see how it immediately affects the energy production. So you can go and find, you can see how it's calculated, losses, shading, near, far terrain shading, etc. And then you basically go and quickly, because you have this information, you go and quickly basically find the worst performing blocks, which from an energy standpoint, right? So you can see, you can even like speculate a bit, why is this happening, do some additional analysis, but that's it. Then you jump to the next floor, basically discipline, which is electrical engineering. You're like, okay, let's apply a trunk bus solution to our layout. So you define the way how the combiner boxes needs to be placed. So what's the pattern you're gonna use, and essentially you just run trunk bus solution to the layout. And after that, you just basically, as you do this, you can see all of your cables in the model. So they're being generated. They kind of, because of the level of details, you don't need to see them all the time. However, if you get closer, you'll start seeing every single cable, which is again just there in the tool, right? So what I mentioned before, intelligent objects that know where to be shown and where they need it. So so then we do an analysis. Okay, let's find the worst combiner boxes, like the basically highest voltage drop combiner groups. Here we are. So, and then let's say we have a specific client requirements, and those are about 1.5% voltage drop, and let's optimize layout. And so you go further and you just optimize layout. And again, just, wanted to show something in the 4 minutes, so like less than that, essentially the workflow we were imagined when we started building PVFARM, where like couple of disciplines work together simultaneously, basically jumping back and forth and basically checking results and moving further with the metrics and with the right kind of insights for the right decisions. So usually when people ask us about the value and where we see the biggest kind of hidden kind of needle movers, and we love to talk about this specific scheme, which very simple in fact, and it's about what are the most expensive blocks from a different discipline standpoint. We see many projects where civil engineering team thinks that those are on the left and right are the most expensive blocks. So essentially this and this. And then you can see that electrical engineers think that this and this are the most expensive. And then structural engineer has their own opinion about, not opinion, it's actually kind of, it's actual data, numbers, right? So everybody is right. So these are truly the most expensive blocks among those disciplines. However, when you start kind of collaborating and start summing up those numbers, you might be surprised that the most expensive blocks are actually not highlighted by any team, which is the place where that's why we're talking about like workflow needle movers, because those are the places where it's hard to see they're happening in between the handovers between different disciplines, right? So, and it's really not that easy, taking into account the complexity and the rush people constantly doing those layouts on the run, on the fly, and whatever amount of time is available. So essentially, it's really hard to spot, but this is the place where like huge opportunities might be left on the table. So essentially, this is why, as I mentioned, we usually think about solar PV project more like a labyrinth of choices, right? So you the project is like entering labyrinth. There is a starting point, and you basically start, and you have like many different exits. And each of those exits, it kind of represents a different design outcome. And every path has its own obstacles, problems, opportunities, and same context and different, way of designing will give a completely different layout. We also like to compare this to origami, which is basically what you see here, same project, and essentially the difference in like 23 millions, 22.5 millions, although it's completely the same context, and we're going to talk a bit more about this. So again, one more visualization. As we mentioned before, we basically said there are 4 disciplines. Like typically people think about civil, electrical, structural. There is a performance modeling, which is the main, but performance modeling in a way, it's a kind of metric of the layout, right? So basically whatever you put in the layout from civil, electrical, equipment, structural standpoint, it produces the energy output, which basically more like a kind of judge number for your layout in general. And that's why we usually create like a layout kind of discipline, which you can call spatial or access design. So basically, because it's extremely difficult to design all of those disciplines simultaneously, typically it's a choice which one will be leading the project, right? So which considerations should be taken into account as early as possible, which should be taken into account next, what kind of trade-offs we need to check, and stuff like that. So let's try to build a couple of examples just to show you on a kind of project which we made up, a little bit bigger project. We just wanted to show what's going to happen if you will kind of prioritize or optimize for one discipline or another. So let's go to the next slide. So as you can see here, we intentionally chosen a site, what we usually call is a interconnection constraint, meaning that you have more land than you need, right? So that's usually the perfect place to play around and to find the best layout from one or another standpoint of view. So same site, same target, 17-18 acres to 30 megawatts DC, and then different order of design. So let's say when we started like with spatial design first, we figured out there are some roads, there is a substation position, we tried to keep it nice and compact. So as a result, we got like layout, which is basically located in here, and it was nice, compact, approximately the same distance to the furthest blocks. We got our number like to 206 millions to build this one. So then that's an example when the spatial access design drives the overall layout design. So then the next approach we used, it's a civil balance of system first. So as you can see here, we just analyzed, and apparently that wasn't a great place to actually place trackers. So basically we run it on the side. We found the best, like the cheapest spots to place trackers in order to get to 30 megawatts DC, and we got to 201 millions. So then we thought, okay, well, what if we're going to design electrical cost? And then we basically make a perfect blocks in accordance with our electrical pattern, which basically worked the best, take into account constructability, and made like perfect rectangle, which was actually fit quite well in this particular project, and we got like number, right? So, and then the last approach was basically structural first, and I will talk a little bit about each one of those, and basically that gave a different number. You might say, okay, so the difference in between like the cheapest and the most expensive 5 millions, which is basically 2.5% on a capital cost, which is crazy. What can be found if you simply just choose the right order of design. And it's even more to that because we didn't take into account some important things. We'll talk about it in a sec. So yeah, just a little bit of explanations. Again, spatial access, you can see, despite the fact that it was the most kind of compact place, there still was a huge gradient. That's why we got like overall crazy cost. But then this one, because we knew that there is a huge gradient needed in here, we basically allocated layout around this road. So we basically got a civil BOS first, different layout, right? So then electrical BOS was simple. We just basically designed, you can see here, perfect block, and essentially, allocated on the layout, connected things, electrical BOS first. So with the structural BOS, we thought, okay, how do we optimize for structural other than, let's say, using the longest tracker would be, let's say, the cheapest one. And then we're like, okay, we got the first option here, and we checked how many exterior trackers, basically how many trackers, exterior and edge trackers exposed basically to the wind, which basically will make our piles more expensive. And then we, based on these assumptions, we actually kind of used our sub-areas functionality to kind of to push it in the different areas. So we find this perfect spot where layout was as compact as the first one here, but this particular bit, because of the road here, wasn't exposed to it, so we moved it kind of in here, so which gave us the basically the most efficient structural configuration. But it's funny, for this structural configuration, could actually trade-off is that you can see that the gradient for this one. So we won basically on a structural config like 300,000. But however, when we run gradient, it was like a 4 million difference, and this option was 4 million more expensive. So again, you can see the order of the magnitude and the swing, and you can see that there are like millions of dollars in the capital cost based on those like different considerations for, like, let's say right now it's average size project. So so basically, couple of examples where drone needle movers or drone workflows were selected. Again, you can see $112 per watt versus $3 per watt. That's simple. So if your layout is driven by a civil engineering team, that would be spotted right away, right? But if it's a electrical engineering, this might be, some of it might lost, and like there are different ways where how you can kind of skip this one. That's why it's crucial is to basically define the order of design. So basically we started thinking about, okay, so order of design is important. How do we define it? So we tried to connect the order of design to the context of the project. So we thought, okay, so if we have like different types of boundaries, different types of terrains, we should already have some good hints about what we should start optimizing for, right? So that's why we started kind of doing some research. So realized that, okay, there are like 3 types of boundaries that are already introduced to you in the beginning of this webinar. And then we also kind of usually define that there are many cases, obviously, but we usually say that there is either abundant land where you have an interconnection constraint, or it's a tight fit where you have a land constraint. So essentially, we usually kind of break down all of our projects in those 2 buckets. And then we thought, okay, in terms of terrain, we can also, and we intentionally don't add any numbers here because those numbers are very specific to every single company. But basically we thought, okay, so we have flat and simple, rolling and moderate, and hilly and complex. And by doing so, we created kind of matrix for, let's say, interconnection limited case. And we put those disciplines, civil, electrical, layout, structural, it basically, it's different. Even like when it's close, it's still different, but it might be a good guidance. So for example, if you have a simple terrain and then big boxy and easy boundaries, it actually makes sense to start with electrical right away as soon as you get your buildable areas. And then as you start with electrical one, so you know that, okay, here's our ideal blocks, we basically can start mixing those up and like making like a proper layout. And on the same side, if you have like a complex terrain, big box and easy, a medium chunky puzzle, you need to start with a gradient basically, and then doing like a cluster strategy. And essentially, sometimes you basically, quite often you need to do iteration. So that's kind of, we the findings we saw when doing this type of research. And as a result, just like some kind of recommendations that can be built within every company with the right tools, like a basically default guidelines on where to start when making certain layouts. And you can also here, you can see on this particular example, same DC target, but different overall cost. And basically depending on how you start and what kind of you optimize, you might end up with completely different layouts. So those like kind of tight fit, length limited matrix as well, those could be built for every single company with a nuances of their operations and things like that. And this is why we usually think about iterations as and needle movers and workflow needle movers specifically, that those are being defined first by leading discipline, that basically working on the layout and starting with the layout. So basically this is the first discipline that the layout is being optimized for. And then within those disciplines, you usually can dive in depths. That's the analytical kind of depths we were talking about, and I'll show an example in a second. So that's the analytical depths we were talking about in the very beginning. So so you can dive in it within each discipline, and then basically by going through the order of this design, you can find the most efficient, the most basically robust layout in a way. So, and this is example of how the analytical depths might be achieved with a specific discipline. Let's say civil. If we will take a civil discipline, we usually, there are like a bunch of ways how you can address this, right? So first flow, you can see scenario number one here is that placing trackers on the terrain, running cut fill analysis, and basically then removing those that are the worst. So removing those that requires the most grading. As a result of removing like single trackers, you will have a very like, I would say inconsistent absence of trackers through the whole layout. So then you would need to reblock it simply because some of those trackers were blocked, and you would need to reblock it. And as a result, you get quite an efficient civil engineering. However, the electrical engineering might be super expensive due to, those ugly blocks essentially. So another scenario, which is kind of similar but different. So here we run basically cut fill analysis for the blocked layout, right? So basically we have a layout which basically trackers grouped into combiner groups, and then let's say central inverter transformer. So we have a properly blocked layout, and then we're removing the blocks which basically requires the most grading. So essentially it adds basically consistency, and it kind of preserves the fact that some kind of the holistic electrical design, because you're removing the whole blocks, but as a result, it's not going to be the most efficient civil. However, in this particular case, this option was much more preferable than this one. There was a huge kind of crazy terrain. That's why the numbers are crazy. But essentially, you see, like you can do the same kind of civil analysis, but basically preserving or thinking about electrical, not like all the way, but in some way. And as we all know, like we engineers who working on such problems, that there is no like a perfect ideal, the most efficient solution. That there are always trade-offs, and basically by doing such a workflow, you can still be efficient with civil, not as efficient as here, but you will be more efficient with electrical, and as a result will be more efficient basically with in general with like overall cost. So essentially this is how we usually, and I will just show like some illustration quickly how it works when you basically running in depth and like using different workflow to kind of achieve the same result with a completely different cost. So essentially those kind of workflow needle movers are crucial, on top of parameters which are basically, swing the cost on a discipline level or in between disciplines, what we call local and global parameters on needle movers. There are also very important third category, which is a workflow needle movers, because based on the context, site, terrain, based on the client's requirements, you would need to optimize different discipline first in order to get the most efficient layout. We've tested it on many different projects, and so try to come up with a framework which we're going to share after this webinar. So the framework, how to define needle movers, as well as some workflows considerations. Again, those are not obviously cannot be used for every single project, and it's going to be different for every single company, but it's more like a framework to use and to figure out what's the best way, how to squeeze the maximum value, especially right now when we have sites are uglier, terrain data and surface is crazier, and basically right now it feels like there is a need in the industry for squeezing basically as much value as possible from the sites, and there is no way to do it with the workflows we used to work, and that's basically this driver is the main reason why we try to find a framework that will work better than what we used to do in the past. So yeah, that's basically my closing thought. Basically, needle mover first mindset means starting with the most critical strategic decisions, not the easiest, not the most familiar, not how things were done, but with the most critical. And when those get right early, then the rest of design falls into the place. So yeah, that's all my presentation, guys. Appreciate your attention. So now let's go and talk a little bit about questions if you have so.
Yes, thank you, Maxim, for the presentation. We are now entering the Q&A portion of the webinar, so you can submit your questions in the Q&A box on your screen. Let's see, our first question is asking, what does it mean to be structurally optimized first? Does that mean minimizing pile lengths? What does that mean to you?
Basically, yeah, that's a good question. So it basically means, yeah, that's a fair question, because it's typically it's typically not what's the most like popular, but however, you can think about layout from a standpoint of how many trackers exposed to the wind. Those trackers that are exposed to the wind, they will have the heavier piles. So in certain conditions with the poor soil conditions, you might actually having like layout with shifted trackers because you need a DC. This will actually result into having extremely expensive piles. And so basically having layout that optimized structurally first, it's a compact layout that basically prevents having like hundreds, like maybe thousands of trackers exposed to the wind. So basically keep this as compact as possible in a way, but also using like the cheapest structural configuration, which might be the longest tracker, or like a different foundation, essentially. Yeah, that's a good question.
Mm-hmm. Okay, cool. What is the maximum size of a solar project that the tool can design?
So the actual, I would say 1 gigawatt, if we will include all disciplines together. If we will include layout only, that's going to be even more, but 1 gigawatt, pretty confident. With the right laptop, it can do it. Yeah.
Okay. Next question, does the PVFARM, does the platform run energy calculations?
Yes, it does. It does. We have a runtime energy model, and what it means is that our energy model works all the time. Essentially, whenever you make layout or change some trackers or move some objects, it's actually going to update energy model on the background, so no need to press any button or anything like that. And also, it's going to work if you place trackers on the terrain or like use terrain following trackers. So we do have energy model, and it's working in real time, basically as a metric for any given layout.
Okay. You talk a lot about using the rule of thumb. So do you have, what is the criteria for row spacing for a rule of thumb?
Interesting. I think it depends. I think no, it's a good question because it depends on geography. I think like people that build solar farm in Texas or like Phoenix, they have definitely their own rules of thumb. So and it depends also what kind of system you're using. Is it fixed tilt? Is it single axis tracking system? What configuration? What tilt? So there will be essentially many kind of inputs that will define this. But I assure that every company that builds the solar PV farms, they will have their own rule of thumbs for a different geography and for a different racking system they use. So
yeah, definitely. AI is obviously a hot topic. So how is PV Farm using AI to maybe do better design options or anything? How are you using AI?
great question. I love this one. We actually, we promised ourselves like 8 months ago that we're going to build meaningful AI. So we didn't want to connect just a large language model in order to have just a chatbot, which is not smart one. And we just wanted to have something meaningful. So we decided that the first low-hanging fruit is that we wanted basically AI to be able to run some workflows. So right now in PV Farm, we actually have a beta of our agent layout. We call it Generation Exploration, GNE agent, which basically can generate layouts for you based on your recommendations and requests. So that was the first goal. But then now we're trying to make it more like educational, basically help people to navigate, help through the platform, as well as like help people to understand what kind of workflow needs to be followed. So essentially, the purpose is to decrease. We can again. This all depends on the industry, and solar PV is a fast-growing industry. And what we see is that new people that come into the industry, they actually like our super users, they actually teach like students newbies on our tool, basically in order to understand all of those trade-offs. That's why we were very focused on educational part of the agent, and that's right now it's a combination of we focused on the educational part. So we basically train the model on our data points, on our workflows, on our understanding what does it mean to have a great design, and as well as like we basically teach it to run some workflows with our algorithms. So it's a sophisticated mix, but we have a beta, guys. You can sign and test it yourself.
Perfect. Remember, you can submit questions in the Q&A box on your screen. We have some time for just a few more questions. Here's a question that maybe you can just elaborate on. It starts off, it seems for medium to high terrain projects, you advise to optimize for civil and structural, and maybe electrical kind of takes a back seat. They're asking, what is the cost trade-off? Do you have a demonstration for this, or do you have any comments about that?
Yeah, we actually, I think like basically it's going to be the answer to the question, it depends. So we saw some projects where civil optimizing for civil works was saving like 30 millions, and then optimizing for electrical was saving like 7 millions. So basically in total, it was more efficient to optimize for civil. However, we also saw the actually opposite cases where the civil wasn't that bad. That's why there was worse optimizing for electrical. So it's kind of, it depends on the context, and essentially I can basically share. I think I will reach out and I will share a bunch of examples. We definitely have those.
Perfect. Okay. Someone is wondering, is PV Farm, is it limited to design, or does it also have pre-construction and construction planning?
So I would say at the moment it is limited to design and a little bit to pre-construction, because we do pile binning, but mostly I would say our sweet spot is design 10, design 30%, with some disciplines we can go all the way up to design 60%, like slope adjusted pile point plan. However, we want to go further and we want to develop like truly vertically integrated tool. That's why the plans as we go is to basically to go as close to construction as possible, and ideally to participate in construction. Yeah.
Okay, perfect. Well, I think the rest of the questions have kind of been answered already in other questions. So I think that is, we'll wrap it up there. After the survey, we would appreciate if you could please take a moment to fill out the survey that's going to pop up, because we do use that feedback to improve our future webinar programming. As a reminder to everyone, this webinar will be shared with you afterwards, and you can view it again at your convenience. You can find PDFs and everything that you need after the webinar. So I would like to thank Maxim for being here, and of course PVFARM for sponsoring today's webinar. And thank you to everyone for joining us today. I hope to see you at more Solar Power World webinars in the future. Thank you.
Thank you.